So it's really a great pleasure to be here today and to kick off this edition of ICAP. I think that everybody will agree with me that ICAP was very much in demand, was very much missed, and really I would like as first speaker to give very special thanks to Michael, Gordon and Joseph and all the ICAP staff actually for their extraordinary commitment over the last years and really the standing effort to bring us today, all of us here in Toronto. So just let me please give you a very special thanks. Yes. So since the last ICAP in Barcelona 4 years ago, let's see if it works. Yeah. Many things happened in the advances of ultracold quantum science and technology. And many of them were under the keyword of programmability and addressability, so bringing the control very much at the single atom level. And so these type of advances have actually, had the consequence to narrowing the watershed between what is quantum simulation and quantum computation. And in this type of topic, another very essential keyword is interaction. So, and we actually would like not only have the control, the full programmability and the single particle control, but also we would like to master the interaction between many particles in the quantum regime. And so if you think about the ultra-low temperature and we consider neutral particle, there are two major native interaction into the system. One is the contact interaction and the other one is the dipole-dipole interaction. And now these two are very different. And for example, the contact interaction is effective only at short distance and it's directional independent. So contrary, the dipolar interaction has a peculiar angle dependence that make them actually directional, so meaning anisotropic, and also effective a long distance with the position dependence. And so these two native interactions are in all the major platform of neutral atom that we use. And so, but the relative weight between these two interactions might be very different from contact interacting gas, which are, let's say, very much dominated by contact interaction to ground state molecule and Rydberg atom, which actually are very much dominated by the dipolar long-range interaction. In between these two extremes, there is a new class of atom, which are, let's say, gathering a lot of attention, which are these highly magnetic lanthanide atom, like erbium and dysprosium in particular. So here you have the situation in which you have these two independent sources of interaction that you can, let's say, that can compete one to the other, that they are of a similar weight, can, sum up or subtract each other, and this gives rise really to new type of phase of matter. In particular, when these two interactions really counteract and the system is maybe slightly attractive, there is another source of interaction that play a role. Indeed, the mean field is not enough anymore to describe the many particle system. You need to go beyond this mean field treatment and the mean field interaction, and there is the first order correction, which is quantum fluctuation. It's only repulsive, and importantly, it's increasing very fast with density compared with the other interaction. And so these these three different sources of interaction are playing together to give us new type of phase of matter. And one example came in 2016 with the observation of what is now called macro droplet. So since if you now put the interaction slightly attractive, what does it mean? That for the many body setting, it's actually convenient to increase the density in order to decrease energy. And so there is an inherent instability into the system. And so the system would maybe collapse, but actually this is where quantum fluctuation come up, giving us an example of a new phases which is really due to beyond mean field effect. And so the system increased the density, but then at some point quantum fluctuation operates as regulator, not allowing anymore a fast growth of the peak density. And so there have been a lot of debate so on how to actually describe quantum fluctuation, and there are some let's say experiment and theory that agree very well, some other that agree less, and also this type of physics is also very relevant in non-dipolar mixture, which have been studied in few laboratories. And so what we did recently is to use this concept which have been used in a non-alkali gas of block oscillation to try to get, an interferometry of quantum fluctuation. Indeed, if you now prepare a dipolar gas in an array of 2D system, and then they let block oscillate under the effect of an external force, like for example gravity, the dephasing of this oscillation tells you a lot about the interaction. And so by looking at the dephasing rate, actually you clearly see that you need to have beyond mean field effect to really, let's say in the theory, describe the experimental observation. And the shift between mean field and non-mean field prediction is kind of a direct way to isolate quantum fluctuation. And somehow we could confirm that sometimes the mismatch observed was not about how the quantum fluctuations were observed. Maybe there is some other effect that need to be taken account in the Hamiltonian. I will come later to that. But also let's think about, okay, that's in the case of non-macro droplet, and now if we were asking ourselves, okay, what happens if we prepare 2D dipolar quantum gases, an array, and now we make the interaction slightly attractive such that we enter in this macro droplet regime. And so now this is just a curiosity which I found very nice. What we observe by decreasing the scattering length is that all these atoms get actually pushed and focused in just one 2D layer. This is an interaction-driven mechanism to create 2D system, which I think is very nice. And you can see this, how the ground state is changing, the interference pattern that you typically have in blockos. So you typically have in 1D lattice is washing out, and actually the process is reversible. So if you ramp back, you see the interference pattern coming out. And that's kind of similar to superfluid to multi-insulator transition in terms of the observable. It's totally reversible, and you can have a single plane. But then if you now don't have the magnetic field in this direction, which makes that the dipolar interaction is attractive along the long axis, but you rotate. Now, again, the phase space density, the phase diagram is very rich, and you see other type of phases that will emerge. And so if you now consider to produce a dipolar BC with the magnetic field in this direction, so locally there will be line of attraction. They would locally try, to increase their density. And so what you can see for dipolar quantum gases is that there is a phase transition, and the system has now broken two symmetry. One is the global phase coherence, so there is phase locking, and the other one is the density modulation. The system spontaneously create this type of regular modulation. And so this system was observed in dipolar quantum gases by the group of Tillman-Fau in Stuttgart, Giovanni Modugno in Pisa, and my group in Innsbruck. And you see this is where the translational symmetry is broken only in one direction, and very recently we also observed the same type of physics in two directions. We have two major observable. One, you can in situ see really the modulation appearing, and then by doing interferometry, matter wave interferometry in time of flight, we can get out the phase, let's say the interference pattern, and probe the phase coherence into the system. And there are many things we have studied, also the other group, and we in Innsbruck. I just would like to remember you the ingredient to supersolidity in dipolar gases. So the ingredient is that you need, let's say, a non-local interaction such that the Fourier transform has an explicit momentum dependence. And so that means that also the spectrum of excitation have a momentum dependence. And now this is in the simplified, so this is in the case in which you get this minimum here, which is called a Roton minimum in analogy with superfluid helium. And that this minimum appear not because there is an interaction term at this momentum, but is more, let's say, the competition of the different energy growing and decreasing that, let's say, drill this minimum in the spectrum. And then we have, so this was predicted by Maciek Levens and Jara Schlapny for Luis Santos in 2003, and we have observed in our experiment about 15 years later. And here, that's the first ingredient. The second one is to ask ourselves, okay, but what happens if this gap closes? So that the Roton minimum completely soften. Then you would say it costs no energy to create excitation. So as soon they are thermally populated, they will exponentially increase. And we were expecting to have a very unstable gas, but by now you know already that probably that's not the case. And so what you would see is that spontaneously you have this little modulation starting to appear. If you do the Fourier transform, you have two major peaks at the Roton momentum in the interference pattern. And then the system was actually not unstable, and these are, let's say, due to the quantum fluctuation, which I have first pointed out by the group of Tillman Fau in Stuttgart. And you see that there is a very fast growth of this population in the side peak, and then a much slower dynamic, which is only due to, let's say, losses into the system. And so now if you put all these things together, all these ingredients together, you get this new type of state where spontaneously a gas is producing this density modulation. And now so the existence of two invariance breaking, I mean, is kind of mapped out also in the spectrum of excitation, which show two phononic branches, one for each broken symmetry. And so there is the soft branch, the lower one, which is the superfluid, so there is really matter moving, let's say, while the stiff branch up here is the crystal mode. It's like just an example, like accordion rigid type of oscillation. And so this, this spectrum was then revealed both in Innsbruck, in Stuttgart, and in Pisa. And then we can ask ourselves, okay, we have two broken symmetry, which one broke first? And so this was actually our question, is the phase coherence or it's the modulation? And to do this, you need to start with a state that has no coherence and not modulation, and so from a thermal gas. And here come to our special way in Innsbruck to study supersolidity, which is that we can directly cool the system, so we really do the thermodynamic transition from a thermal gas condensing in the supersolid state. Okay, it's just decreasing thermal energy. And so by cooling down that we can do, and you can see now what this was one of the early experiments for thermal gas, you get from phase contrast imaging, this modulation. And so what we observed, as I told you, we have observable for phase coherence and modulation. So, and what we observed is that actually the density modulation seems to appear before the phase locking. So it seems from a thermal, you go to a crystal, and then you go to a phase coherent supersolid. But then, okay, this was cooling a thermal gas. What about heating? I mean, if we heat up a quantum fluid, if we start from let's say a condensate, and we just heat up. And here we saw something extremely strange, I have to say, because if you look here in this life cycle of our system, here I'm plotting the modulation, and here the number of condensed atoms, and the color scale is the temperature. Now just draw this line at 1. If I move at constant condensed atom, but the total system is more hot here than here, you see that actually the cold system have no modulation in this case. And actually by heating up, you get the appearance of modulation. I have to say we didn't see this coming, and was thanks of Thomas Paul in Harus and his collaborator that now we have a sense for this. And actually what they observed is that if you now do the ground state calculation at 0 temperature and a finite temperature for some specific value of the parameter, you see that at 0 temperature you don't have modulation. When heating up, it's finite temperature. Why this? Well, I already told you that quantum fluctuation is really important. It's a new energy term in your Hamiltonian. Also, thermal fluctuation exists, and they are equally important, and they go opposite to quantum fluctuation. Quantum fluctuation is stiffening, thermal fluctuation is softening your system because of the interaction between the excitation and the condensate. And then you see it very clearly, but that by just reducing the temperature, the Roton mode is going down, is softening toward crystallization. And the hole that I'm showing now here, it's in a linear chain, and now we were asking ourselves, what is happening? What is happening if we now we try to go from a linear to a more two-dimensional type of system? We were very much inspired by work in ionic Coulomb crystal. And actually there you see a structural quantum phase transition from a linear chain to a zigzag, just opening the transverse confinement in ion. And we took this idea for our, let's say, extensive system of many, many particles. And now if we go one by one, just opening the trap, you see that actually at the beginning it's kind of working. You start to have a type of zigzag, but then you lose the supersolid state. It becomes again unmodulated. And actually we found that the important thing is to take this idea, but to maintain the trap density, so number of atom and frequency constant. And so this is what we did. It was a major effort because to increase atom number in the system was not so easy. And so this was a linear chain. And now we kind of start to increase the atom number and opening the trap. And you start to see that it's appearing like two, and here is more zigzag. And then if you further, open, you start to have even a little bit more extensive in this type of surfboard trap, as we call it. And now, very recently, we made a major update in our experiment to have circular optical trap. And so this is now where we see hexagonal, let's say two-dimensional supersolid, where we checked also the phase coherence. And now, I mean, that you have a circular state, that you have how many circular state, so, okay. Now that you have a circular state, you can do many things, because this is, let's say, cylindrical symmetric. And we like cylindrical symmetry state because of, the angular momentum is really well conserved in this system. And so, of course, the first thing one would like to see is vortex in a supersolid state. And so actually this vortex, there are now starting to a very interesting theoretical paper of how to do vortex, so how to observe and what would be the vortex in the supersolid, which is a relevant question because the superfluidity of a supersolid, so far, it's kind of, stated indirectly in our experiment by looking at the phase locking in a many-body interacting system, but we don't have direct observation like the beautiful vortex experiment done with alkali atom, or like, Gretchen-Chambal persistent current. So this is what we still need to do, in my opinion. But, the problem is that even in non-modulated state, even in dipolar normal quantum gas, vortex have never been observed. And this is not only, let's say, an extension to what have been done in non-dipolar gases, because actually vortex in dipolar gases are expected to have many, many new other features, like a larger vortex core, maybe density ripple near the Roton instability, or like I'm showing here, some anisotropy in the vortex distribution instead of an abricos of lattice. Really, you have interwaved high-density vortex line, high-density vortex line. And so, and this is what I will now show you, because again, and this is amazing, in dipolar quantum gases, you can use the interaction property to create vortex. How do we do this? Actually, this was a proposal coming out in 2019 by Parker Martin in the UK. So let's just think about the fact that if you have a gas and a magnetic field in this direction, as I show you, atom would like, to align along the magnetic field. So globally, so a gas, a dipolar BC would extend a little bit. And this is the effect of magnetostriction, which have been observed in chromium many years ago by the group of Tillman-Fau. So the system is magnetostricted. And now, if you rotate the magnetic field, you start to get in the plane an elliptic type of elongation. And now the idea by Parker and Martin was to start to rotate the magnetic field. So much easier than rotating a trap, which for me as an experimentalist is kind of nightmare, although beautiful experiments have been done. But here we have only to rotate the magnetic field. And so here's what you see. So we start with a circular trap, let's say really cylindrical symmetric. We rotate our magnetic field. We start to rotate. We are increasing now the rotation frequency, and so the elongation gets larger. And then when we keep going with the same rotation frequency, so you see that the system is starting to nicely rotate. And for a low angular frequency of the rotation, the system is following, is getting elongated, and then start, to rotate. But if you now start to increase the rotation frequency, you see that the system first nicely follows, and then at some point something happens. At some point, it's not energetically favorable for your quantum gas to follow rotation. He wants to respond differently to this imposed angular momentum. And now I show you here our data for just example for increasing angular frequency. You see for lower one it follows nicely. Then at some point you see that something is happening. It's getting deformed. It doesn't like anymore, to simply follow. And here is what is expected in our theory. Now we have large rotation frequency, large meaning on the order of the trap frequency. So this omega is in unit. And then you see it start to be spiralized. You lose atom. Now you might already see that something is happening in the low energy region, low density region with this kind of vortex appear. And now the vortex are trying to enter in the high density. 2 minutes, yeah, I'm okay if I find the one. And then after a while, I just put it here, the vortex start to enter into the system. And now we did this experiment, and these are now our, let's say, theory and the observation in our quantum gas. And so you see that atoms are lost. First, spiralize a little bit. You have a low density rugosity with some vortex being nucleated there, and then they try after a long time. This is 1 second. Our system is very, so we have enough atom at this longer time, and you see the vortex entering. And also, if you now change a little bit the interaction parameter and the atom number, the theory is predicting the stripe phases, and now those are the observations that we have in our system. You really see that you have this high density line, and then the vortex, you don't are kind of seated in between this line, and if you don't have the magnetic field tilted, but you put it back, the stripes are gone. And of course, the next step is to do it with the supersolid. We have not yet observed vortex, but we start to magnetosteer our supersolid, and you see if we just, rotate the magnetic field, you see a little bit of elongation, and then if you now change phi, how our state is kind of rotating. So more will come, I hope. So there is much more in lanthanide atom that having a large magnetic moment. Sorry, I have to go back. That having a large magnetic moment, if you're interested, there are 2 reviews that we put together with colleague, one more on lanthanide and one more on dipolar physics. And I also would like to highlight that there is a lot going on also in lattice physics and tweezer for Rydberg, erbium Rydberg tweezer, and there is a poster by Sam White today, this afternoon. So with this, I hope to have shown you some of the interesting features that dipolar quantum gases can give us. I would like to thank the team that, that we did together this journey in understanding this system, our collaborator, our funding. I also, let's say, to point out that we have new opening, just check all our website. And if you are, let's say, interested in long-range interaction, we have now, with Antoine Breuer and Robert Lowe, we are organizing in Innsbruck a workshop on long-range interaction from Rydberg to atom light to magnetic, everything that is long-range ion, and still few days before closing the registration. So thanks a lot for your attention, and yeah.
Thank you for this wonderful and inspiring talk. Can you grab one, please? I feel like there's a feedback on you. You can also just raise your hand to ask your questions. No need to step up to the microphone. Yes, Bill.
Yeah, so you mean here. So this is the plot. You can plot the aspect ratio as a function of the rotational frequency.
Right, and the magnitude of the field is staying constant. You're just
Your magnitude of the field, it's like in a dipole trap, when you rotate the dipole trap and you start to rotate it faster, the dipole trap, you also have that the elongation is kind of a Coriolis force in some sense, it's getting more elongated while you are, spinning faster and faster. And this is more or less the equivalent. But at some point, this breaks down, and this is where the vortex. Yeah.
And when you see the vortices come in, the pictures that you were showing, were those in situ pictures?
Yes, exactly. These.
Why are the cores so big?
Yeah, actually, it's a very interesting question. So there are two aspects: the physical and the technical. So the technical aspect is that these are not really in situ. It's just 3 millisecond expansion, okay? And to see it a little bit, so just a little of expansion. Our resolution is finite. That's the fate of experimentalists. And and you see that we indeed observe really less vortex than in the theory. I mean, just because of resolution. But there are very interesting papers from Alessio Recati and from Sandro that actually predict that the vortex core should be much larger in the supersolid, actually in the more studied in the supersolid phase, due to this kind of stretching of the anisotropic interaction.
Okay,
Thank you.
All right, so one more correction starting now. I will repeat the question for online audience. I hope I don't butcher your beautiful question too much, but I'll try my best. Other further questions? Please.
I also have a question about this part. Naively, I will think as you are rotating the magnetic field too fast, the dipole gas cannot fall because it starts to see some average effect of that rotating magnetic field. So I was just wondering, when you start to see kind of the drop of this threshold of the aspect ratio, the rotation frequency compared to the energy scale of your cycle moment is about what's the
The square root of the trap frequency, which is where more or less you expect the instability to appear.
Do you also see heating effect due to this rotation?
Also, you see, sir?
The increasing of temperature of your cells.
So no, actually we don't see the increase of temperature in our trap. Of course, we rotate for 1 second, and so the lifetime is limited again. So you will have some loss of atom, but we don't see an increase. Of course, if you now start to rotate faster than the trap frequency, simply the trap don't hold the atom anymore. But we are not going. So the instability that we are speaking about is occurring a bit before. Yeah.
Great. Are there further questions?
Can you somehow observe that if you go to the kick-in of Fermi-Magnetic theorem, namely that if your range of interaction somehow shrinks sufficiently that there's no symmetry breaking into D? Like, is it possible to observe such things?
I have not understand the physical picture.
I mean, if the range of interaction is sufficiently small, the Fermi-Magnetic theorem tells us that in 1 and 2D there's no symmetry breaking. And so can you kind of observe this kick-in of this kind of physical phenomenon?
So what do you mean for range of interaction? Really, now this is the point of where it's how it fell down, or
How it falls down is this.
yeah. So we have that is 1 over r to the cube in our case. So that's the dipole-dipole interaction. There is not too much that we can do. Now I don't know if in cavity experiment with light cavity experiment like the super nice experiment in Tillman-Esslinger group where the range of interaction, but this is larger. Now, I don't know, in 1 over r you mean. So this, so dipolar is 1 over r to the cube. There is, without dressing, there is not too much we can do. Maybe changing the dimension, really. That's a good point, yeah.
Maybe let's have one more last question. Please.
Yes, in a gases, people manage to put a single vortex in the system.
What is very complicated?
Why don't you produce a single vortex?
We can do. I mean, it's just a matter of parameter. So in the non-alkali, you had the single vortex. This was the first super nice paper from Jean Dalibat. Maybe that's also, and others, I guess. I mean, I don't know I recall this particular paper. But then what you can do, for example, is to, have a situation in which really the trap frequency and the rotational frequency and the protocol allows you to create many vortex. And now these many vortex, like the one that have been also observed in alkali and then also in fermionic, so they have so it's just, you can explore many different regimes depending on how you change your parameter in some sense. Yeah.
Great. Let's thank Francesca again for a wonderful talk.